Hello everyone, my name is Ali Han. Today I'm going to present the topic about open sets and closed complement. The main idea of this presentation is that a set in Rn is open exactly when its complement is closed. So basically, we are going to study the relationship between open sets, closed sets, and the complements. First, let me briefly introduce why this topic is important in mathematical analysis. Open sets and closed sets are very fundamental concepts. They appear in many topics, such as continuity of functions, convergence of sequence, compactness, and the structure of Euclidean space. A simple way to think about this is open sets describe points that still have some space around them, while closed sets are often related to continuing limits points. In this presentation, I will prove the relationship that A is open if and only if the complement of A in Rn is closed. And I will also explain the equivalent for A is closed if and only if the complement of A in Rn is open. Now, let's set up the space we are working in. Here we work in Euclidean space Rn. This includes a familiar space such as R, R squared, and R cubed, and more n-dimensional Euclidean space. For points x in Rn and a radius r bigger than 0, the open box centered at x is denoted like this. This means all points whose distance from x is less than r. Also, for sets A's complements in Rn is denoted like this. This just means all points in Rn that are not in A. Now, we recall two important definitions. First, a set A in R belong to Rn is called open if for every x in A there is a r bigger than 0 such that there is a ball belong to A. In simple words, every point in an open set has a small open ball around it and that stays completely inside the set. Next, we use a sequential characterization of closed sets. In Rn, a set F is closed if and only if every convergent sequence in F has its limit still in set F. So, if sequence F belongs to F and xk converges to X, then the limit X must also belong to F. A simple way to remember this is a closed set does not lose the limits of its own convergent sequence. Now we state the main theorem, just like we mentioned at the beginning. Now, let's look at an example in R squared. Consider an open disk A. It's look like this. This means A is not does not include the boundary cycle, and its complement is like this. And this means the complement contains a boundary cycle and all points outside the disk. So this example shows the idea clearly. The open disk is open and its complement is closed. Now we prove it. We prove the theorem. First direction is the sufficiency. Suppose A is open. To prove that the complement of A in Rn is closed, we use the sequence characterization. let xk be the sequence in the complement and suppose xk converges to x. Our goal is to show that the limit x is also in the complement. We prove this by contradiction. Assume a sequence of contradictions that x is in A. Since A is open and x in A, by the definition of a set, there is some radius r bigger than 0 such that there is a ball belong to A. Since sk is convergence to x, there is n in N, that's natural number, such that for all k bigger than A, the norm of xk minus x is less than r. Therefore, sk belong to the ball and the ball belong to the A for all k bigger than A. This contradicts with xk belong to the complement of A in Rn. So therefore, our assumption xk is false, x in A is false. So every convergent sequence in the complement of A in Rn has its limits in the complement. Therefore, the complement of A in Rn is closed. Now we prove the another direction, the necessity. Suppose the complement of A in Rn is closed. We prove that A is open. Now let's x in A be arbitrary. We need to show that there is the ball like this. We still assume a sequence of contradiction that there are no such R radius exists. If no such radius exists, then no matter how small the ball around X is, it cannot be completely contained in A. So for every k in N, the ball is not contained in A. Therefore, this means that for each k, we can find a point yk such that yk belong to the ball and yk is not in A. Hence, yk is in the complement of A in Rn, and the norm of yk minus x is less than 1 over k. Now, since the norm yk minus x is less than 1 over k, we have yk converges to x. Since the complement of A is closed and yk is in the complement, it follows that x is in the complement of A in Rn. But this contradicts with x in the A. Therefore, there is r bigger than 0 such that there exists a ball belong to A. Hence, A is open. Now let's explain the converse form. We have already proved that A is open if and only if the complement of A in Rn is closed. Now we replace the A by its complement. Then we get this. Since the complement since the complement of A in Rn is A itself, so we can guess A is closed if and only if the complement of A in Rn is open. To summarize, the main results is that open sets and closed sets are deeply connected for any sets A in Rn. The A is open if and only if the complement of A in Rn is closed. Also, A is closed if and only if the complement of A in Rn is open. This result is important because it allows us to describe many ideas in analysis, and either in terms of open sets or in terms of closed sets. The proof mainly uses three ideas: open balls, convergence sequence, and proof by contradiction. So overall, the theorem gives us a very useful bridge between open sets and closed sets. Okay, that's all for today, my presentation. Thanks for your listening.